Hi, how you doing? Let's go ahead and start our today's experiment. Then let's have a look. So today's experiment, this is our fourth experiment of the class or the course. The addition and resolution of vectors using the force table. So in today's experiment, what is the objective of today's experiment? Then today we are going to learn a few things: how to add vectors and how to resolve a given vector. Okay, we already covered the analytical part of this in our chapter 1 vectors video, so we're going to focus on two items today. How do we do this using a simulation, because we are not going to conduct this experiment practically in a lab, rather we will be using a simulation. And the other one is like, how do we add vectors using the graphical method. All right, so having said that, what are the equipment that we need? So according to the manual, what do you need? The force table. We're not going to conduct this experiment in a lab, so therefore we don't need any kind of force table. Okay, so then this thing is going to be replaced by a simulation. What else do you need? You don't need a string. Do you need a protractor? Yes, that's for the graphical method. Do you need a ruler? Yes, for the graphical method. And then of course a graph paper is also important to do the graphical method. Okay, so once again, like the theoretical method is already covered in the vector graph, or in the vector video in chapter 1. Then I'm just simply lightly just touch it and then just directly move to the practical part of the lab. So you can go ahead and then watch that part just to do the analytical part of the experiment. Okay, so therefore in general, like, how do we add vectors? What are vector quantities? Those are already covered like in the theoretical part, so I encourage you to watch those videos. So then there are different ways of adding vectors, especially when it comes to the graphical method. Using the graphical method, you can add vectors using the triangular method, and you can add vectors using the polygon method. In the triangular method, what do you do? What you normally do is, like, you may have a set of vectors, like for instance, like, let's say you have vector A and say you have vector A, and vector A is like this. Then you may have like another vector. Get back, and let me use an arrow. So mostly vectors are represented by array. That means like a line that has an arrow on one end. So let's assume that you have vector A, something like this, and you can call this vector A, and vectors are represented mostly by a bold letter and an arrow overhead. And let's say you have another vector, and then let me use a different color, and let's say vector B. Then if you have vector B, and let's say vector B is around here, rather let me change the direction of vector B. So say vector B is something like this. Okay, then this is vector B. Then if someone asks you, like, find vector A plus vector B, and let's assume that the resultant vector called R, then using the graphical method, what you can do is you can have two vectors. Okay, so what you can do is just like you have vector A and then vector B, then the first thing that you need to do is connect the vectors head to tail. Okay, then the vector that runs from the tail of the first vector to the head of the last vector, that vector is called the resultant vector. Resultant vector means the sum of the two vectors. So therefore, like, what you're going to do, or what you will need to do is just basically you will go ahead and then you have the vector, and what you can do is, like, if you can, you try to move that vector and bring it close to centered. So what you can do is bring it right there like that. So that means now you have vector A and vector B just connected head to tail. And then the resultant vector is going to be the vector that's going to run from the tail of the very first vector, and then it goes to the head of the last vector. So the one that I just used like a different color here is known as like the resultant vector, or this guy. Okay. Then the angle, this theta of the angle can be represented by something known as like theta. Theta is represented by tan of inverse of the resultant components in the y direction divided by the resultant components in the x direction. For this particular simple example, of course, your theta angle is equal to tan inverse of just simply the magnitude of vector B divided by the magnitude of vector A. Okay, so this absolute value symbol that you see, in the vectors, it means the magnitude. Okay, so this is a simple way of like representing or solving vectors just using the graphical method. Okay, so but when we get back into details, then we're going to see like using the given parameters and the examples in the manual. Okay, so and then there's also a polygon method. The polygon method is like, what if you have like more than two vectors? Like, then in that case you are going to form a polygon. That means like if you have 2, 3, 4 vectors, like something like this, and let's say you have vector A and vector B like this, and vector C running like that, then the resultant vector is going to be again the one that runs from the tail of the first vector to the head of the last vector. Okay, and that vector is known as the resultant, or the sum of all those. So in this particular case, vector D, which is the resultant, sorry for failed to show you. So you have vector A, vector B, and vector C. They are connected head to tail. Then vector D is the resultant, and vector D normally represents the sum of those 3 vectors. Okay, so in this particular case, the 3 vectors formed, in addition to the resultant, formed a polygon. Okay, so pretty much those are just pretty much the same thing. So then the analytical method, again, I'm not going to go to the analytical method. You can go through the theory in this given in the material. You may use a Pythagorean theorem, the Pythagorean theorem if you want, but also you may use like the cosine method in some instance where the two vectors are not perpendicular to each other. Then you will have to apply some kind of a cosine law. Okay, so you can go through the this example and everything, like as you can see here, like how the resultant is found using a Pythagorean theorem if you have 2 vectors that are perpendicular to each other, the way you see them here, vector A and vector B. But if the vectors are not perpendicular to each other, then what do? Then most likely you're going to use the cosine method. But what if you have more than two vectors, and how do you solve or find the resultant using the resultant of those 3 or more vectors? Then definitely you will need to apply the component method, which is way more easier and more direct than applying the Pythagorean or the cosine law like every now and then. Okay, so having said that about like those are simply just the analytical method. Okay, so then the experimental, we're not going to conduct any experiment as we said, but rather we are going to use some kind of simulation. Then based on that, we're going to solve the problem. So without further ado, what I'm going to do is like I'm going to show you like how you are going to carry this particular experiment. So there's a table here, particularly data table. Then we're going to use this data table. Okay, so in the data table there are three methods that you need to apply to find the answer. Okay, so therefore here is the procedure. This is how you are going to proceed. First, there's a graphical method. I'm going to explain how you are going to use the graphical method, and there will be analytical method. Then the analytical method, you need to go through the Victor video to understand and do it. The experimental method, then I'm going to show you like what kind of simulation or website we're going to use. Okay, so now first thing first, here you can see, like as an example, force 1 is given as 0.2 G. It says here, like for instance, I'm going to circle it here, this much amount of Newton. Okay, so for simplicity we're going to do the following. Then lowercase g that you see here for gravitational acceleration, we're going to use 10 meters per second square. We're not going to just kill ourselves trying to approximate like 9.8 and try to approximate the forces on a graph paper. That's going to be very difficult for us. So there is we're going to use g throughout this experiment as 10 meters per second square. Every time that you see lowercase g, then what it means is like multiply the number that is in parentheses multiplied by 10. Okay, that's the easiest way to do it. Okay, so the first thing it says, like, let's assume that you have two vectors. One vector is 0.2 times g Newton, and it's acting at 30 degrees, and you have force 2 is acting at 120 degrees. Then therefore the procedure is going to be like this. So basically you have two forces. Then one force 1 is acting, like, let's say it's acting at 30 degrees. Let me use some kind of, so 30 degrees, okay, something like that. This is just like, how do you measure the angle? So make sure that like you are measuring the angle with respect to the positive x-axis, and of course you have to go counterclockwise. Okay, so counterclockwise approximately along the x-axis, starting from the x-axis. This is how you measure the vectors. Okay, the vector video explains this well, so without any problem you will see it. So you have force 1, which is equivalent to 0.2 times 10. It's going to be 2 Newton. And then you have another force, then force 2. I'm going to use another color for easier. And then it says like force 2 is acting at 120 degrees. About 120 degrees is approximately something like this. Then the angle for the second vector is this, and that green angle that you see is 120 degrees, and this is force 2, and which is 2 Newton. Then now you're asked to determine like what is the resultant, or what is F1 plus F2. The three different methods, that is the graphical, okay, and then there is the analytical, and the third one is of course the experimental. Okay, so for the analytical, then you follow the theory that is covered in the lecture video. In the graphical method, what you're going to do is you're going to use the graphical method. So the graphical method is you're going to use the following steps for the graphical method. Okay, so if I'm going to use the graphical method, okay, for the graphical method, this is what we are going to do. The first thing is, what you need to do is come up with a scale. So the first step is you need to come up with a scale. So you need to have a graph paper, and you need to come up with a scale. What do you mean by a scale? It means like 2 Newton, force 1 is 2 Newton. It's very difficult like to put it on a graph. Okay, so therefore, if you want to put that value on a graph, then you must come up with a certain amount of a scale. Okay, so a scale in essence that, like, what kind of scale. Let's say, for instance, for this particular case, we can say like 2 centimeter, or for instance 2 centimeter equals 0.5 centimeter, 0.5 Newton. So 2 centimeter on a graph is equivalent to 0.5 Newton. Okay, if that is the case, then you know that this shows you what does it mean for every centimeter. What are you going to get? So in other words, like force 1, which is 2 Newton, right, then is going to be equal to how many centimeters? So for every Newton that you have, like what we know is, like for we get 0.5 Newton for every 2 centimeter. So to put it on a graph, then you can cancel this by this, and then 4 divided by this is going to be 8 centimeter. This is my scale. If you think like 8 centimeter is too big, probably you may go with 1 centimeter equals 0.5 Newton. Okay, so likewise, if you do the same kind of explanation, then you will have force 1 on a graph paper is going to be equal to 8 centimeter as well, because force 2, because force 2 is also, use a different color for it, also 8 centimeter. Then now the next step, what you're going to do is the following. What you're going to do is you're going to go ahead and draw the two graphs. So let's assume that this is the origin for your graph. Then what you're going to do is use your ruler, okay, and your protractor, measure 30 degrees, and then draw a line, maybe a line that goes probably along here. So let's assume that this is where the 30 degrees, and then use another ruler, or the same ruler. What you're going to do is, then as we said, like, let's go ahead and then draw vector, the first vector. Then let's say you measure 8 centimeters for the first vector, and 8 centimeters is approximately, let's say it's up to here, okay, up to the arrow. So that is where your force 1 is. Now, according to the graphical method, I tried to mention it, like you connect the vectors head to tail. Then what you're going to do is the second vector is going to be starting where? At the tip, at the head, right here, at the head of it, at the head of the first vector. Okay, and then you measure 120 degrees. 120 degrees means, using your protractor, you cannot just know what 120 degrees, approximately, let's say 120 degrees is up to here. Then now you go ahead and then you draw your second vector, okay, then at the start of the head, okay. Then this, the length of this guy is, in terms of it, like it's 8 centimeter, we already said it, okay. So again, the magnitude of force 2 in terms of centimeters, as we said, it is 8 centimeter. Then now, using the graphical method, what you are going to do is you are going to draw the resultant. Now the resultant vector is like, start from here and end it where? Here. Okay. So therefore, I'm going to go ahead and draw the resultant vector. Then the resultant vector is going to be like this. Okay. Then this is your resultant. Then measure the length of R. Okay, so now once you do this, what you will do is measure the length of R, you know, the line, that's what I mean. Okay, using your ruler. That value is equal to R in centimeters. Okay, in centimeters. Then now you need to find, then using the scale that we applied. What did we say? 2 centimeters is equal to 2 centimeters equal to 0.5 Newton, right? Using that, right, the scale, then convert the centimeter for R to Newton. Okay, then that's literally what the result of the vector is going to be. Okay, but that only gives you the magnitude, and then you need to find the angle. Then you may say, like, how am I going to find the angle of the resultant? Of course you have your protractor. What did we say about the resultant of vectors? What we said is, like, you measure the angle with respect to the positive x-axis in the counterclockwise direction. You measure that, and let's call that theta for R, using your protractor. Voila, that's it. You found your resultant vector using the graphical method. Okay, that's how you will proceed. So I I'm going to quickly show you, like, you know, how you are going to do for the second and for the third. Probably, like, you may still ask questions like, how am I going to find those things? Once again, please pay attention properly, and then how am I going to use it? Then preferably it's good you stick with the same scale. Okay, so vector addition 2 for the second part, that means for this part you have f1 0.2. you know what I chose is, like, you know, because I like to graph my things like on a bigger kind of thing, then I chose, probably for the last one you may use a smaller scale, I mean for the 3 vectors, but for those 2 I prefer what I said is, like, 2 centimeter on a graph paper represents 0.5, but that's my scale. Okay, remember, it's not mathematically, not saying like 2 centimeter equals 0.5 Newton. No, on a graph. Okay, on a graph, when you graph it. So then for the second vector addition, okay, so f1 is 0.2. I'm going to switch to the whiteboard in a moment once I get my data. And f2 is 0.15 g, and the angles are theta 1 is 20 degrees and theta 2 is 80 degrees. Okay, so let's switch to the whiteboard. Then now your fourth one is 0.2 g. I already said it, like, use g as 10 meters per second square. Okay, since that's the case, then your f1 magnitude is going to be 2 times 10, which is, 0.2 times 10, which is 2 Newton. Then f2 is going to be 1.5 Newton. Then if I'm using the same scale, I'll be using the same scale as I said it, like, which is 2 centimeter for every 0.5 Newton. So remember, this is my scale. Okay, this is only a scale. It's not like a valid mathematical equation. It's not. So that means in terms of centimeters, then what am I going to get is, my F1 on a graph paper will be equal to, again, 8 centimeter, right? Because I already showed you how to convert that. Then F2, which is 1.5, it's going to be 6 centimeter. How did I do this conversion? Look at like the previous one, how I did it in the previous case. Okay, then what am I going to do is I'm going to go ahead and then translate those on a graph paper. And theta 1 is 20 degrees and theta 2 is 80 degrees. Then once again, I'm going to draw my vector. The first vector is going to be, I'll take my protractor, and then at 20 degrees I'm going to draw the first vector. First vector 8 centimeters. This is an approximate. I mean, I'm not properly using 1, 2, 3, 4. Let me use something like that. So let's say this is 20 degrees. So remember, how do I know? I'm using a protractor. You must use a protractor, otherwise you will not know. And how do I know? This is the length of this line is 8 centimeters. Okay. Then I'll go ahead and put my second vector here. Then I'm going to measure 80 degrees. 80 degrees is going to be somehow something like this, right? Approximately. Right? Then I'll go ahead and then draw my second vector. My second vector is going to be like this. It's going to start from here, but it cannot be more than the other one. This is what? This is how many centimeters? This is 6 centimeters. This is for F2. This is for F1. Now I need to find my resultant. Easy, once again. Your resultant must run from the tail of the first vector to the head of the last vector. That's it. This is your resultant vector. What do? Use your ruler and measure the length of R. Okay? Then using the scale, this is scale, convert how many newtons that value is. And you need to find the angle of the resultant. So every vector is expressed both in magnitude and direction. How do you measure the magnitude? The magnitude is whatever you calculated from centimeter, you convert that to Newton, and then that's what you get. Okay. And the angle is always measured with respect to the x-axis. Okay. So with respect to the positive x-axis, you measure that angle, and then that's how you find it. Okay. This is how you determine it. What if you have 3 vectors? Again, if you have 3 vectors, that's also just not a problem. You go ahead and then add 3 vectors just simply together. Okay. The only thing is you need to stick with your conversion, and that's pretty much it. So as an example, then how do you do vector resolution? How do you do vector resolution? Again, this is also you can do this as you're studying. What it says is you need to find a vector resolution for a force of 0.3 times g Newton. That means 10 times 0.3 is 3 Newton if the angle is 60 degrees. In this particular case, what you are asked to find is what are the x and y components of that vector. Okay. When I do it using the experimental, you will see it how simple this thing is, and then it's going to explain everything, and then you will be able to see much of the work. Okay, so then what is happening here is for the third one. Once again, let me take my given. For the third step, you have the force, magnitude given at 3 Newton, and the angle that it acts is at 60 degrees. In this case, you have to find the resultant. Okay, so using the graphical method, so far I'm talking about the graphical method again. So the graphical method, what you're going to do is just simply use the scale. I'll be using the same scale again. We're going to stick with our scale. So according to our scale said, I'm going to use the same scale, 2 centimeter for 0.5 Newton. I think this is a better way to write it instead of saying 2 centimeter equals 0.5 Newton. So what are you going to do here? What you're going to do here is for 3 Newton, you're going to have, you do the conversion and everything. How many centimeters you have? Like, you're going to have 12 centimeters. Okay. Then here, what we're doing is vector resolution. We call it vector resolution. Vector resolution is different from vector addition. Vector resolution is like converting one vector into its components, into its x and y components. That means, what if I convert this single vector into 2 vectors that can give me the same impact as this single vector, but those 2 vectors are one acting in the x, the other one acting in the y direction. Okay, so again, you'll use your ruler and your protractor, and then you'll go ahead and then draw a vector. What is the length of this vector? It is 12 centimeters on the graph. You must use a ruler, otherwise you cannot find the length, or what you're doing is completely wrong if you're not using a ruler. So, and then you must use also a protractor, otherwise it's not going to be right. Then once you have that vector, the next step is going to be, you need to find its x and y components. How do you do that? Then first you need to have, just random xy axis. Let's say this is your x axis, and you have your y axis. Okay, now you need to find its x and y components. How do you find x and y components? So basically what you're going to do is draw a vertical line, right? Draw a vertical line that coincides with the x-axis, and then draw a horizontal line, probably that coincides with x-axis. Okay, let me use another color, maybe a blue one, and that one will run from here. He was moving it. All right, let me get back to you. Let me use arrows. So this is one, okay, the vertical line, and then the horizontal line is going to be okay, my eraser is still on, that's why it is eliminating it. Okay, then again I'm going to draw a line that is the same height as this. So those two are x-axis components, and then y-axis components, and then the x-axis component is just simply again right, no, so this will be the x component. Okay, we delete this. So this is Rx, Come on. Okay, so this is Rx and this is Ry, or you can call it Fx. Actually the force's name is F, so therefore let's use Fx and Fy. Okay, so this is Fx and this is Fy. Okay, then you measure the length of Fy in centimeters and convert that centimeter to Newton using this familiar scale. The same thing, use your ruler, measure from here to here and find what the length of that line is, and then convert that centimeter to Newton using this familiar conversion. Okay, that's what you're going to do using the graphical method. Now let's get back to the experimental method. Using the experimental method, if it was in a lab, what we were going to do is would have just set up the lab and then do everything like in the lab using a force table. There are like lots of force table videos. If you go on YouTube, it shows you how to do it and things like that. You can also read the steps that you need to follow, but read the manual. Of course, you still need to stick with the procedure, but when the procedure tells you the following in the experimental, okay, the graphical, you will be using the graphical. In the experimental step here, when you reach here, it's going to tell you this: on the force table, clamp four pulleys. Pulleys at 30 degree and 120 degree, and attach enough weights to each hanger to the total of 0.2 kilogram, so as to give weight forces, force 1 and force 2, 0.2 g. We already decided that, we already have the table. Okay, in those directions, the weight hangers usually have masses. And don't have any weight hanger, we're not worried about it. We just go ahead and then hang or put a 0.2 kilogram, in other words 2 Newton force in the X, on 30 degree, and 2 Newton force on 120 degrees. Here is where the simulation is. I'm going to attach this this link like in the video. So the first thing that you're going to go ahead and do is you can read this, the instruction, what to do and what not to do, and so on and so forth. This thing is going to literally show you how, everything. You can see your answers, you can see what you have done for the experiment, literally using the graphical method or the analytical method. This thing is going to verify it for you. I'm fine with it. So it's going to show you three random vectors here as a given. We're going to use 3 vectors, right? Definitely. But for the first 2, we're going to use 2 vectors. But for the first one, what you're going to go ahead and do is you're going to come and do the following. So you read all those notes, and then you will have to find where you are going to put in your forces. Okay, so the first thing is this is about the forces. So over here on icon number 2, when you click on it, it's going to show you something like this. So our force 1 is 2 Newton. We already said it. And the angle for our force is 30 degrees. Okay. For our force 2, the force is 2 Newton, and the angle is, we are told to put 120. Force 3, we don't have force 3, so therefore just set that value as 0. Okay, and then come and look at it. This is how the vector looks like. Okay, this is how the vector will look like when you do it experimentally in a lab. Of course, you're going to attach a mass that pulls, this little ring in this direction and little ring in this direction at 120 degrees. Those are the two vectors. And then, right, here it says literally, okay, then what it says is like, using the third pulley and weight, determine the magnitude and direction of the equilibrant. It doesn't say the resultant, because you are finding the equilibrant. So the equilibrant, then there's something which says equilibrant, then here. If you come and click here on number 17, click here. Click the circle to show or hide the equilibrant vector. If you come here and click on the equilibrant, then the equilibrant is there for you, showing you literally. Voila. But if you see here on the manual, it says, remember, the resultant has the same magnitude as the equilibrant, but opposite in direction. That means the resultant is going to be something that is going along in this direction. That means whatever angle that you have here minus 180 degrees, then that's what the resultant is. So in this lab report, I want to see this diagram. I want to see the two vectors and the equilibrant like this. I don't know, take a picture of it or print it or save it as PDF. It's up to you what to do with it, okay? But that's it. So the two vectors are added for you. If you want to show the resultant, it's always pretty easy. I already said, like, that shows you the resultant, but if you want to show, it also shows the resultant for you, or like, just calculate the sum, or the resultant, you can find it so we got the equilibrium and got the components. So you can investigate most of the things, like by clicking the little arrows here, for instance, but those are just more detailed kind of items. But if you don't want, you don't have to. Okay, so this is about the vector. So that's pretty much it. Easy. It just did everything for you. So you got the equilibrant, and you can find the you can see the magnitude of the equilibrant, right? Remember, the equilibrant is opposite to the resultant, or the net vector. I'm going to show you number 12. If you click number 12, that shows you the resultant literally. This is what the resultant is. The one just happens in purple. If you click down here, okay, if you click down here, it's going to, you can also see the values somewhere. Let me see, calculate the sum. Okay, if you click here, it's going to show you like what the resultant is. You see this guy? That's the value. So that's the resultant. So using the graphical method, as much as possible, this must be your resultant. The angle is easy. It's just showing you like the angle is about 75 degrees for the resultant. That's it. Okay, simple. Then for the second one, you will do the same thing, but the only difference here is now what? You have 2 Newton for F1, okay, and then 1.5 Newton for F2, and then you have the angles 20 and 80 degrees. Again, what do? You come here, F1 is 2, then theta 1 is now what degree? 20 degree. F2 is now 1.5, and the angle is 80. That's it. F1 is here, F2 is here, then the equilibrant is here, the resultant is here. So make sure that you need to include this in your work, because I need to see it. Okay, a third force, you don't have a third force, so you don't have to show it. So if you're looking for the value here, it says icon 28, it says like calculate the sum. Now the sum of the two vectors is about 3 Newton, and the angle is about 46 degrees or something like that. Very simple. Again, for resolution, you can do resolution vectors. It's also pretty straightforward. What you have is only vector 1 here, only one vector with 3 Newton and angle 60 degrees. The rest you set them to 0. That means you have 3 Newton here, and it acts at 60 degrees, but F2 is 0, and F3 is 0. In this case, you don't need any equilibrant, so therefore, turn off any equilibrant, and at the same time, you don't need to show the net force or the resultant either. Just simply force one, but there is something which says like the components, so you can see like what components you have. Like for instance, Fx force 1 has x component this much, and F1 has y component this much. Those are the x and y components literally. So you can verify your calculations from the graphical method by looking at the answers here as well. Okay, so your graphical and this should be pretty much the same, of course, and the analytical too. Okay, what if you have 3 forces? Again, simple. 1 Newton at 30 degrees, 2 Newtons at 90 degrees, 3 Newton at 225 degrees. You add them all. Here again, come here, 1 Newton at 30, 90 to 25, right? 30, 2 Newton at 90 degrees, and 3 Newton. Now force 0 is not 0. Okay, then now this is 225. Okay, there you have 3 vectors, 1, 2, 3 vectors, and then you go ahead and then like show the net force, that's the resultant, and the equilibrant in a lab. The equilibrant, that's what you will normally find. Then the details of the equilibrant, what angle it passes through, and so on and so forth. You can come up with that. Okay, so that's pretty much it. Yep, the fun continues. Until next time, just take care.